So let's say, let's see what the mean ergodicity theorem for White's stationary processes is. Now, the aim here is, as I said, we are going to use the time average to estimate the mean of the random process, and we would like to we would like to see the condition under which this is true. Okay. Now, first of all, as with the sample mean, you have to observe that the time average itself is the random variable. Okay. And then we'll compute its mean to see whether it really converges or it approaches, let's say, to the true mean or not. Okay. The first thing to do is to see that maybe it doesn't really go to the true mean. In that case, there is no point in looking for an ergodic theorem. Okay, let's see. Of course, the key observation is, well, the key assumption here is x of t being White's stationary. Okay, we are assuming its mean is constant, okay, doesn't depend on time. Also, its autocorrelation depends only on the difference between the two observations, okay? Therefore, let's say the mean is mu sub x, and let's compute the expected value of the time average. So just plug in the definition of the time average. And then at this point, well, you can take out 1 over 2t out of the expectation. It's just a multiplier. And then you have the integral. Of course, by linearity of both integration and expectation, we can switch them, right? We have done so many times before. So you switch them, you get the integral of the expected value of x of t, which we know to be mu. So plug that in, right? Mu is constant with respect to time, so it comes out of the integral. And the integral integrates to 2t, cancels out with 1 over 2t, and the result is mu sub x. Great. So the mean of the time average is really the true mean. Okay, so what we say is, for a White's stationary random process, the time average is an unbiased estimator for the mean. Great. Now, what we are going to look at next is the variance. Okay, in order for this estimator to be useful, its variance as t grows, as your observation grows, the variance should vanish, right? Why? Because in that case, the time average itself, as the variance gets smaller and smaller, that means the variance is going to go to zero, which will imply the quantity, which is the time average, becomes more and more deterministic, right? When your observation interval gets larger and larger, that means if that is the case, if the variance goes to zero, then the time average itself is approaching a deterministic value, right? Which is the mean itself, which is what we want. So let's see what the variance of the time average is. Now, again, just write the definition of variance and plug in the definition of the time average. The trick we do here is, well, obviously we have two terms here multiplied involving integrals. The first thing we do is, well, we move this minus mu term inside the integration because it doesn't depend on the time, the integration parameter. We can do that also here. And then you see here I'm using a different integration parameter because I'm going to combine these two integrals, okay? Which gives me 1 over 4t squared, a double integral, both of which ranging from minus t up to t, x of t minus mean, x of t prime minus the mean, dt prime, okay? And at this point, again, I'm going to take out this constant, 1 over 4t squared, out of expectation, and then I have, again, integration and expectation, which I can swap again. So expectation goes inside the integration, which gives me, as you see, the autocovariance function of the random process x. And since I know x is a White's stationary random process, I can write this autocovariance as not t and t prime, but just t minus t prime due to White's stationarity. Okay? And at this point, well, I'm going to make a change of variables. Now, let's see, first of all, on the Cartesian coordinate system, let's see what we are integrating, okay? T runs from minus t up to t, and t prime, again, runs from minus capital T to capital T, right? So what I'm integrating is inside this square region, okay? And my infinitesimal area unit here is this, dt, and this is dt, and this is dt prime. This is what I'm integrating with this double integral. So I'm going to change this double integral into a single integral. And for that, I define a u as t minus t prime, the difference between two time samples, okay? So at this point, you see, on this line, u is minus 2t. As you see, this is the point where t is minus t and t prime is t. So u is minus 2t, okay? And as you change, as you shift this line, right, t minus t prime, which we have defined as u, now increases towards this direction. And at this very line, through the origin, it becomes 0, right? And then it goes on growing. And at this line, at this extreme here, it becomes 2t. And my integration will be over this infinitesimal strips, okay? As the infinitesimal area, I'm going to use this infinitesimal strips. And their width is, as provided here, is du, right? And u here, u starts from minus 2t, it becomes 0 here, and it goes on to 2t. So it's a continuous increase in this direction for u, okay? And the infinitesimal area of one strip is, well, the height is du as I have defined it, and the base here is 2t minus the absolute value of u, right? If this is not clear to you, try a few values here. You will see that that holds. And because as you see, it grows up to 0 and then it starts shrinking because, well, u starts growing. Okay, so the infinitesimal area is 2t minus absolute value of u times du. So if you plug that in, right, this here, this along with this together corresponds to this infinitesimal unit area. Okay, I used to have this area here, infinitesimal area. Instead of that, I'm now using this infinitesimal strip as my integration unit. I'm still multiplying that with the autocovariance, but now the autocovariance is evaluated at u because I have defined u as t minus t prime. And then I take one of the two t's here and divide that with this term here, okay? And what I get is 1 minus absolute value of u divided by 2t times the covariance at u integrated from minus 2t up to 2t. Okay, so this is the variance, and I want this to go to 0.